Started. So we are now live. So, welcome to the last lecture. So this time we're going to just review what we have been discussing during this course. Go over through the learning goals that I have for you, and I hope that you have been able to work towards. So, to explain what is needed to pass the course, how much points, and so forth. So let's start. Functions and graphs. We started with that. So the concept of function, these basic elementary functions is basically what we dealt with. Elementary functions being those that you can form with addition, multiplication, then exponentiation, logarithms, the sine and the cosine, and the inverses of these functions, the power functions and so forth. Very large class of functions is this elementary functions, but nevertheless, we might encounter situations where these elementary functions don't always play out. All of our examples and all of our tasks for integrals and so forth are in fact such that you can express them using elementary functions, but there are cases in which this doesn't happen. So that was the first part. Then we talked about limits and limits of a function. They're the epsilon delta, the infamous epsilon delta. That is the key concept. So the concept of the epsilon and the delta, that is absolutely paramount to understanding of the concept of a limit. So if you don't, when I say epsilon delta and you don't know what that means, then that's a red flag. Go there, go look at the definition of the limit of a function. Limit, you should, if I called you on the telephone at the middle of the night after you had been drinking the previous evening, and I call you and you just barely wake up and you answer the phone and I ask you, what is the definition of the limit? Tell me the epsilon delta definition, and you will be able to say what it is. Okay, I'm half joking. You can check it out. I mean, you're at liberty to use this material, but understanding it is actually paramount. I also gave an alternative phrasing for it so that, for every open interval in the that contains the point, which is the proposed limit, there is another open interval around x, such that as long as x0, let's say, if I claim that the functions, if I claim that the limit of f(x) when x approaches x0 is L, then there is for every open interval that contains L, there is an open interval around x0 such that all those numbers around x0 map to this open interval around L. Conversely, for every epsilon, I mean the epsilon delta characterization was that for every epsilon, then for every epsilon there is a delta such that if x minus x0's absolute value is smaller than delta, then L minus fx absolute value is smaller than epsilon. Of course, this must be positive. So that's the definition, and that's what you need to understand. And the definition of continuity, the continuity at a point means that the function's value at that point is the same as that function's limit. And we had these one-sided limits, like limit from the positive and limit from the negative side, and these two coincide if and only if the limit exists. And please study the precise definition of a limit. That's the important thing here. So there's a lot of this soft hand-wavy material where you calculate the function's value at points closer and closer to that. That's all nice, and it kind of exhibits the idea, but that's, in mathematical speak, that's hand-waving. You know, it doesn't really prove anything. Then we had the definition of the derivative. And really, the important part of the derivative is, you know, okay, it's fine that you remember how the derivative was defined from first principles. Like if you want to say that, you know, that the f prime at x is in fact the limit of h to 0 of f of x plus h minus f of x over h. So you can define this as the definition of the derivative. So this is the only place where I am actually diverging from the definition in the book, in my teaching. And I want you guys to really, you know, you can revert to this. This is fine. If this is the only thing you remember, then fine. But it was rather more important, in my perspective, to understand that a function is differentiable if and only if at point x, if and only if the small perturbation, so moving by h from x, the value you get is f of x plus then something that is directly proportional to both h and the f prime of x plus then error h times absolute value of h times r of x and h. So the idea here is that there is the error, and the error term goes to 0, tends to 0. And that's the differentiability definition that I wanted to use. And I wanted to use this because then from this, you can define this f prime of x. You can find this f prime of x using the limit as h goes to 0. Right. So this definition of differentiability doesn't talk about the graphical intuition or the tangents and the so forth. We don't have to draw, you know, lines or the secant of the curve and then do the limit at where it only meets the curve at one point. Those are all fine. If those help you remember it, then fine. Just, you know, go through those definitions. They can be found in that book, and you can learn it through that. But I really do think that the more powerful, mathematically powerful, you know, and I'm making a fist here, meaning that it's really raw power here in terms of thinking and algebraic thinking in these terms, is that the function f at x plus h is, you know, you are where you are at x, so that's f of x plus then just a linear change. F prime of x is a coefficient, and h, you know, you linearly move. And then there is an error term, which when h is small can be ignored. So great many things that we did during this course was based on this realization. And this is differential and integral calculus. So I want you to understand that the concept of differentiability is that when you are dealing with small enough changes, then you can, any function looks like it's linear. So that was the important thing. And then there were the differentiability rules. The derivative as a function, you can think of it as f prime of x, that's the function. Differentiation rules, chain rule was the prominent one. Then there was the product rule, the power rules, and all those. You don't have to learn them by heart. There's a table of derivatives and table of integrals at the end of this book, and you can refer to that. What is more fascinating and important is how and why they can be derived from these first principles. That's the mathematically educating part. Not remembering, you know, the derivative of the sine is the cosine, or the derivative of the cosine is the minus of the sine. So, you know, you can, all that can be looked up in the book. Of course, it's more fascinating that you can actually derive this if you have enough time and energy to do that. The implicit differentiation we skipped. That is, in retrospect, something that might have been there, maybe. I would have taken that, but we had the series and the sequences that had to be taught. It's in the curriculum, so that was the one that I skipped. I decided to skip. Exponential and logarithmic functions, they work pretty nicely. The idea of the derivative of the inverse function, I really do urge you guys to learn how to do that. All of those, actually all of those rules, learn how to prove them. That's the main thing there. Not really on how you differentiate. Applications of derivatives, we didn't talk a lot about this. We didn't talk a lot about this. I skipped much of this, minima, maxima, all that stuff. I mean, you guys probably know already that the minima and maxima are found at the edges of a closed region or at places where a derivative is zero. So you know that already, and even if you don't, then I'm not going to ask it in this exam. And you know, I wanted to have this idea of what we're dealing with is this differentiation in a theoretical sense. There was the L'Hopital rule, and we kind of talked about that. And really, that was the important thing. I mean, if you don't remember what the L'Hopital rule was, there are several difficulties. I've for some reason, I've grown accustomed to writing like this. If there is anyone who speaks French here, you may be familiar with the history of the different alliteration or different ways of writing this. It is my understanding that the French spelling of, well, basically hospital has changed over the years. So that's the rule is pretty old. And it was basically that if you have the limit of f of x over g of x, and if that's 0 over 0 or infinity over infinity, then that's equal to f prime of x over g prime of x. And the justification of the L'Hopital rule, really, I mean, I gave you that idea or the justification in the zero case, if it's 0 by 0, because if we are close to 0, then f at x plus h, so f at 0 plus h is in fact pretty much equal to f at 0 plus f prime at 0 times h, right? And if f0 is 0, then that goes away, and if g at 0 is 0, g plus 0 plus h is roughly equal to g0 plus g prime 0 times h. And now you know this, if you take the quotient of these, if you divide this f with this g, then if you use this approximation, then f prime 0 over g prime 0 is the only thing that remains. So that's the justification of the L'Hopital rule in the 0 over 0 case. The infinite over infinite case is a little bit trickier. It's a little bit trickier to prove or to justify, but you know, not much. You can look it up. There was also the Newton method, which had its own chapter here. I didn't take this. We only introduced it as one of the exercises where we generate a sequence, and then the sequence then converges to some number. It was based on this approximation using derivatives as well. Then we talked about the integration. So integration as in terms of defining an area, and there we use the Riemann integral. So the Riemann integral is how should I say? There's this Finnish term called karvalakkimalli. And I have no idea how to translate that in English. And there's no Finnish speakers in the audience. So, well, if there's any Finnish speaker here who knows how to translate karvalakkimalli in English. The intended meaning of that is that it's like something for the common folk. So it's nothing fancy. It ain't much, but it's honest work, if you will. The Riemann integral works when we're dealing with continuous functions that have no visible pathologies, so to speak. Elementary functions that behave nicely, you know, law-abiding functions, nothing weird. So if they're not weird functions, then we can use the Riemann integral. And the Riemann integral was defined as the limit of that particular sum. I'm not going to recite that now. Please learn that. Please learn that and understand that, and understand why it is so. Especially understand why, if you are dealing with the function that is continuous, then you can use any point on the interval when the interval goes smaller. And it's crucial to understand that in that case, we're doing the Riemann integral because we defined it in such a way that we take these smaller and smaller blocks, and the blocks beginning and end approach the same point. Obviously, when the blocks become smaller and smaller, there's just at the limit, it's just one point. Then we can take any point in that interval and the results limit will be the same. But this assumption cannot be made unless the function is continuous on that interval. So if the function is not continuous, then it does matter which point we take. Take, for instance, the function that is the step function. You know, it's 0 at negatives, and at zero it jumps to 1. Or even worse, let's take the more extreme step function. It's -1 when it's negative. At 0, it's 0. And at any positive value, it's +1. So you take any interval that contains the 0. As long as that interval is an open interval, it can be closed, but as long as it's not non-trivial, so it contains both negative and positive numbers, then it's radically different whether we choose 1 or -1 or 0 as the point, right? So it can amount to 0, it can amount to -1, it can amount to 1. So let me give a very, very weird example. Take a function, and you don't have to learn this, but I'm just giving you an example why Riemann integral is not the end all be all of integrals. Take the function, which is, let's say it's 1, okay, let's say it's 0 at every irrational point. And at every rational number point, you take the reduced form of the number, so it's P over Q. And let's say we're talking about numbers between 0 and 1 only. And it's P over Q. And if both P and Q are even numbers, sorry, they cannot be even, it's in reduced form. If they're both odd numbers, then it's -1. If one of them is even, then it's 1. So this is absolutely horrible function. It zigzags between -1, 0, 1, and so forth. Definitely no way to integrate this with the Riemann integral. Yet there are ways in which we can ascertain that its integral over that region is in fact 0. We can actually integrate it. But that's not the point in this course. My point here is that learn the Riemann integral, but be aware that definition can be made far better and far richer, because the function doesn't actually have to be continuous. It just has to be continuous because we're using the Riemann integral. We're using that limit definition. Never mind that. There were linear approximations and differentials. We didn't talk about those. Oh, sorry, I was skipping. So definite integral was that limit. The fundamental theorem of calculus is very important. We went through that proof, and really you should understand what is going on in there. So the integral from any point A to x, ft dt, its derivative with respect to x is in fact f of x. So that means that it's justified to call the integration the antiderivative in some sense. I dislike that characterization, but nevertheless, it is justified. So that fundamental theorem of calculus is really important. We used it a lot, implicitly and explicitly. And then, you know, integrals involving different kind of functions, exponential, logarithmic, inverses of trigonometric functions, and so forth. Not a heavy fan of these complicated integrals. There were some situations which I think merit certain ideas. We used a little bit of time to look at these integrals. I wouldn't worry about those. I'm not, if integration of things like, you know, try the square root of the tangent function. So the square root of tan x and take the integral of that. It can be done, but it's ridiculous. So you see what I'm pointing at here is that very quickly after a couple of simpler cases, these functions become horrible. Horrible enough to merit not doing it by hand. There is some virtue in doing that, but yeah, no. We didn't talk about that much about the application of the integration areas between curves. We did talk about that. We didn't determine volumes. I skipped much of this. I skipped the hyperbolic functions as well. In retrospect, I would have liked to have talked about this, but like I said, this time schedule is just quite a nightmare from that point of view. So read this if you like to learn more about it, but I'm not going to ask these things from you. Then moving on to the next volume. So in short, all chapters except chapter 6, and in chapter 4, really only the L'Hopital rule. Maybe look at the limits at infinity and asymptotes. You can look at the linear approximations as well. We used that kind of everywhere a little bit, but I didn't cover that during the lectures that much. So really the L'Hopital rule from chapter 4 and the antiderivatives, really those are the things that we used anywhere in any sense. And chapter 6 you can skip. Sorry, I'm trying to get to here. And in volume 2, basically, you know, sections 1 and 2 were basically there already. So didn't take chapter 2. I asked you to maybe read that in one of the agendas for the week, but we didn't cover that. I'm not going to. Questions are not going to be from that part. Techniques of integration, really integration by parts. So it's the product rule of differentiation, and then just flip it over in antiderivative, and then you know you need to rearrange it so you get integration by parts. Trigonometric substitutions work for, you know, square root of x squared plus 1 and so forth. Turned out I put one weekly exercise that turned out to be much harder than I had originally thought, and that happens very easily. Just change a couple of parameters, divide by x, multiply by x instead of divide by x, or you know, divide by x squared instead of x, and so forth, and quickly everything blows apart. So, you know, let that be a lesson. Let that be a lesson to me, you know. Choose the B instead of C instead of the B, and you know, you get Horrible. There are all these memes in over the internet where you see, okay, this is the kind of exercise, this is the kind of integrals that your teacher gives you in the exercises, and that's like, integral of cosine of x. And then this is the kind of integrals that they give you in the exam, and then there's the integral of the square root of the tangent of x. That's actually a standing joke in some math groups that I follow, that, find the integral of the square root of the tangent of x. Okay. Anyhow, look at those ideas, use them if needed. I'll try to make sure that any exam questions are such that they can be done by hand. And when done by hand, if I expect you to show the calculation instead of just an answer, I will say, use substitution and give me at least 2 or 3 stages in order to show that you know how to do that. Not going to do a lot with that. Numerical integration, we kind of skipped. Improper integrals meaning integrals that go to infinity. We did use those a little bit, but we didn't talk about that that much. So yeah, that's not going to be asked in the exam. Then there was the differential equations. So differential equations, basics of differential equations was, first order differential equations, separable differential equations. I skipped the direction fields because numerical methods, because I felt like that's kind of not in the spirit of how we cover other things either, so we're not going to do that. There are ways to do numerical calculations for even the most complicated of partial differential equations. I mean, several variables and then different differentials there, but not in scope for this course. Really, there were 3 classes of first order equations. The first order linear equations, the logistic equations, well, that's a little bit more complicated, but it has a closed form solution and it has this S curve. It's called a sigmoid. So sigmoid functions are very important in many branches of mathematics. They're used in describing growth and describing certain asymptotic behavior and so forth. They're also used in machine learning as activation functions because certain sigmoid functions have this nice property that the derivative is fairly easy to calculate when you know the function's value. So the function's derivative is always a simple expression in some cases, of the value of the function itself. It comes from the fact that you have an exponential function both in the numerator and denominator, and if it's a suitable form of function, then you get the derivative is easily expressed in terms of the function itself. And obviously, because of the nature, it's really already because, the logistic equation had this form: P prime at t is in fact equal to P times 1 minus K over P. So this was basically the how it was defined. So you now immediately see that if this is a differential equation, but it's also a nice thing if you have a solution to this, then the derivative is easily calculated if you know the value of P, because it's a solution to this and it's a simple algebraic expression. So that's one of the reasons they use it in machine learning. Because when you need to do the derivatives, you need to figure out the partial derivatives of a sigmoid function and so forth. If you study that field, then by all means look it up. It's actually a fascinating field, but not really differential equations, but these functions appear there. We kind of went a little bit back and forth. So I skipped these sequences and series and instead moved pretty much to this, where we talked about the second order linear differential equations. So you can skip all, this book 3, only the chapter 7 really was at play. I wonder if it says here, only chapter 7, yeah, it says that. Chapter 7, second order linear differential equations. non-homogeneous version and homogeneous version, and then basically a tutorial on how to solve those. We didn't go through these series solutions. We talked about the applications a little bit. You should be aware of them. The canonical example being, you know, the RLC circuit. There are other examples as well. I mean, there are definitely several examples of second order differential equations from various points. You know, spring or pendulum systems, they have this, very often have this second order differential equation kind of characterization. You can describe many such systems using second order differential equations. And then the last one, again, having to go back, the series, sequences and series. Looking at the series and sequences, divergence, integral, comparison, alternating series, and then the tests. We skipped really the power series. I was going to cover this during this last week, but really we ran out of time. So here we are. I would have very much liked to have talked about this, and let's just very quickly look at this. I mean, we have time, but this is not going to be the exam, but I'm just going to just go through here in terms of power series. You know, you can think of the power series, which is kind of like geometry. It's basically, it's a geometric series, but one where the constant coefficient there may change. So this kind of series, Cn times x to the n, is known as a power series. And it's like a function of x. It depends on what this x is. This kind of series is very often used in finance, where x is then, you know, the C1, C0, C1, C2, that's the net cash flow, and x is basically the rate of return. And then, you know, this function, you find out the rate of return that makes this 0, so that's your break-even rate, rate. So if your rate is above that or below that, that kind of depends. It may be, it is possible that, you know, your cash flow is in the future. So the C0, C1, let's say that these C's with small n are negative, and then, you know, the larger C's come only at the end. But if this x is very large, well, small, depends on how you view this. Actually, this x is actually usually of the form is somewhat differently expressed, but the idea is that they tend to get smaller and smaller, these values. It's actually, if there's a rate of return r, then this is usually given as 1 minus r when you're doing discounting. So x is 1 minus r, and it's actually but it's a power series that is applied there. And you can say that it's centered at somewhere else if you offset these all by a. It's a power series centered at a. And the thing that happens is that that you can actually express many functions in terms of these power series. And I'm not going to go into this because it takes quite a bit. There's an area, or there's a area of convergence. You know, the values of x at which this goes towards the radius of convergence, where they go to 0. There are other, and so it depends on what that x is. This is really basic, interesting, fascinating stuff. And you know, then there's the Taylor series, which then gives us a way to. I'm just going to skip the properties because we're not going to analyze it. There was this cash flow, present value of future winnings. That was actually it. So the present value of future winnings is you're in the future you're going to earn something, and you're doing it with like this. So it was one. and going down, expressing these as functions and so forth. And the Taylor and Maclaurin series, then you can express these nicely. You can use these to express nicely, but basically all the elementary functions can be expressed using these. So the Taylor series of the function f at point A is determined so that you just take this x minus a centered power series, and then each term is the nth derivative divided by n factorial. And then it turns out that all of these elementary functions can actually be represented in some interval by this Taylor series. It's called the Maclaurin series if we use 0 as a. I'm not going to go here, but the Taylor polynomials, they can be used to approximate this function. And so you see here, very, very quickly, you see here that in fact, what is happening at point here, you can see that that's just the linear approximation of the function at x, right? When you are moving from a to x. So that's basically f at a plus h, where a plus h is x, so that h is in fact x minus a. And then that's just your first order approximation. Well, the thing is, you can use the second derivative to approximate it better, the third derivative to approximate it even better, and so forth, all the way to nth derivative to approximate it better. And you can actually try this out if you want, if you're interested. You can try this out with polynomials, and if you formulate this polynomial such that f of x is in fact a polynomial, then you will in fact come up with the same polynomial. It's just the derivatives and the coefficients, they churn out themselves from this. So it's actually pretty nice. These polynomials can be expressed, for pretty much all possible functions. They're not very good approximations. They're very good approximations in some region. For instance, here's an example of the sine function, and it's approximated around 0. So if you're approximating it with third order polynomial, it's like this curve, and it pretty well resembles that. Then you're taking the fifth order polynomial, it resembles it very well over here, but then it starts growing. And if you take the sixth order polynomial, it goes all the way here and up, and seventh and so forth. So it starts approximated at the larger, better and better at the larger and larger region. But of course, you have to take it all the way to infinity for it to, at the limit, converge towards this. Sadly, we didn't have time to discuss this. This is actually a fascinating thing, but we didn't have enough time to cover all of this. I think this 7 weeks is a little bit too short for this. That plus we missed one lecture because of technical problems. So yeah, but it's not optimal. I'm sorry I was unable to teach you this part. So that's basically it. These are the topics. Limits, continuity, the definitions, be very careful with that. Derivative, be very careful with the definition, know the definition. Integrals, the Riemann sum, its definition. The fundamental theorem of calculus, to tie the two together. Differential equations. So first order differential equations, separable differential equations, logistic equations, second order linear differential equations that are constant coefficients, the homogeneous version, so where it's, you know, the right-hand side is 0, and the non-homogeneous version, which you can then solve by basically guessing one extra solution, and then you get the complete solution. And that then convergence of a series, of a sequence, convergence of a sequence, and then series, you know, when do series converge? The P series, the power series, the geometric series, the harmonic series, which doesn't converge, tests for checking these. So compare it to the P series, the integral test, an alternating series test. Is it alternating, and does it tend towards 0? And basically that's about it. So with that, that's the course material here. Right. It shouldn't be too hard, I hope. I'm going to try to make the exam questions such that it requires you, all the exam questions, I try to combine two of these sub issues here. For example, there might be a question like, you know, something about the derivative of some function, which requires you to recall the definition of the derivative and how to approximate something in the linear fashion. And then after that, there may be like, okay, let's say here's a differential equation. What can you say about the solution based on what you said before? And it's usually something very simple. So I'm not saying that this is exactly the kind of question that will be, but I'll try to make sure that each of the questions in the exam will somehow try to combine two of these issues in one question. Not to make it too contrived. If it's not possible, then it's not possible. But all these issues like limits and continuity and derivative and integration, well, if it's a differential equation, then it's very easy to come up with a differential equation that requires you to do, for instance, integration. And then when you do that, then that already combines two. So that's set. We may have something like the derivative and then application of the series, maybe. We will have definitely something that requires you to use the epsilon delta engine, you know, to prove something is a limit of something using the epsilon delta. That is definitely going to be there. So I'm guessing there'll be about 4 questions, I think, in the exam. And I'm going to try and measure it in such a way that none of these questions should take more than half an hour to answer. If you know your stuff, probably 15 minutes or less. So if you're actually very proficient in this, the exam questions shouldn't take you more than about an hour to do, less than that even. If you're less than proficient, but you do know your stuff, it should definitely not take you more than 2 hours to do this. And if you don't know what you're talking about, no amount of time will suffice. So I think the 3-hour limit is perfectly reasonable. Okay. So regarding these points, there were 7 exercises. 6 times 12, that's 72 points plus then 10 points. So that's 82-point maximum. So I'm capping that. By the way, I'm capping that number of points because there were so many people who missed. I said I was going to do this. So I'm capping that in the way that I'm only taking, I'm taking a maximum of that 82 minus 12, so a total of 70 points into account. So if you gathered more than 70 points from your exercises, the rest is not computed. I'm sorry for those who were really meticulous about it, but I said that it will not matter if you miss 1 week, and I am good for my word. Also, the curve is not linear, so 70 points gives you maximum, but the difference between 60 and 70 points is not great. And then on every 10 points from that, it's roughly 1 point, 1 or 2 exam points. So it's about, I'm not sure how exactly what the percentage is, but the percentage of total points from exercises is roughly about 40% of the total maximum. And then 60 points comes from the exam, roughly. And then as for grading, if you get the maximum points, all the points from the exam, then I'm probably going to be giving you a, well, if it's an absolute maximum, absolute perfect score in the exam, then you will get a 5. If you don't get a perfect score, you may still get a 5, but after I add the numbers from the exercises. And if you get 1 out of 4, you know, if you take the exam and you get less than half points and you don't get, if you didn't get any exercise points, then you won't pass. But the exercise points will nudge you over the passing limit if you get at least about 25%. I mean, so with the maximum points from the exercises, the minimum passing grade is roughly 25% of the exam. And then as the points go to 0, then the minimum passing goes to up to 50 points. But I'm going to still weigh, so these numbers, after you've passed, the numbers you get from the exam will weigh a little bit more than before passing, right? You get what I mean? So it's non-linear. It's not linear, just like I add all points together, because the grade will be based 40% roughly on the exercises and 60% of the exam. So that's roughly going to be, I have to judge it a little bit different, a little bit non-linearly. So I first judge whether you pass, and after you've passed, then I calculate the points together and to see what your grade is, right? So making a otherwise non-passable exam a passable exam will eat more of your exercise points than increasing the grade. So increasing the grade from, in other words, increasing the grade from 0 to 1 is harder than from 1 to 2, 2 to 3, 3 to 4, 4 to 5, right? So it's non-linear in that sense. And in that, getting from 0 to 1, the exercises weigh a little bit less than the exam, but then when you get to the points, the exam and the exercises have a much closer relationship. Okay, I'll publish the exact form of that function when I fit it into this curve. So these are the I'm not fitting you guys on a curve, so I'm not going to. Another thing, other people's success or failure has no effect on your grade. So this is well, only in the sense that if it turns out that no one was able to solve a particular problem, then I will discard that from there, or if 90% or more fail something. But if everyone knows one thing, then everyone gets the points. That I promise. So the point is that you're not competing against each other here. So no one will get any benefit from others doing badly. That's one of the reasons I hate the idea. I never use it. the idea that, you know, you calculate the people's average and then you make sure that, you know, 10% get a 5 and 10% get 25% get a 3 or something like this. I don't know. Try to fit a curve. I never do that because I don't think that's fair. I don't think that's fair at all. Well, it would be fair if we had the general population, like everyone who doesn't even study mathematics and so forth. Then that might be fair, but not on this course. See what else. I already gave you the dates, so it's Thursday or Tuesday for the exam, and it's 1 p.m. I had decided that before I looked at the latest votes. Just when I watched the votes, it was one more for the 1 p.m. time, and I think it was like 17-16. But then when I had decided this, and I looked at the votes again, and it was now 17-18. So but I had already sent that message, and you know, so. But it's touch and go. The Tuesday time will be also available for you guys. I hope that one of those times is possible for you. So Tuesday the 15th and Thursday the 10th. So I will grade them all in one go. I will grade all of them in one go so that I'm not even looking at the questions before the Tuesday. Do not, if you attend the Tuesday, okay, you had a question, hand up, you can answer. Someone asked did you ask for, deliberately ask for, did someone ask for, I saw that there was a hand up, but now it went away. Oh, maybe it was a misclick. Okay, no mind. So if you want to say something, just use the hand up or the thing, but you know, maybe it was a misclick. Okay, where was I? Yeah, so if you can do it on Thursday and you try it on Tuesday, then sorry, on Thursday. So there are 2 dates, the Thursday and the Tuesday. If you do it on the first date and you feel like you didn't manage very well, do not do it on Tuesday, because the thing is, I will just combine all of these answers into one pool and I will then grade them all in one go. And that's your first attempt. So it's not meant to be your re-attempt of that exam. The reason is that it's, you know, there will be another, I mean, you will have 2 other attempts at doing this, one in January and one in February, which will be given online, just like this one. And the dates will be given pretty soon. I don't know the dates yet, but dates will be given soon. And you can then retry to take the exam if you didn't get a good grade. But this Tuesday thing is not meant for that. It's meant for those who cannot attend on Thursday. So choose one of those dates and do it then. And if you do both, then I will simply discard the Tuesday's answers. So be aware of that. I already mentioned that in the exam, but I'm actually being serious here. I'm only going to grade 1 paper per person. All right. I think that's about it. I think we're all right. Artem, you had something to say?
Yeah, just want to make sure it's online exam, so we can do it from home.
Yeah, yeah, you do it from home, and there is no restriction on materials or software or anything like that. The only restriction, and this I cannot in any way control for, is that you do it yourself. But if you hire someone to do it for you on your account, then I cannot control for that. That's something, you know, it's up, you know. I just hope that no one does that, but I mean, there's no way that I will be able to monitor that. But yeah, you do it at home. It's going to be on Moodle. So you know the link where there is that, which I said mock exam. So it's going to be just below that. And I really just urge you guys to do the following. You do this mock exam and you do the submission. Do the submission here. You can submit on this thing, and try. It's going to be the same thing. So you will be having, of course, it's not going to be this. So you will have this page and you will be able to look at this. This is not the exam, of course. And so this is just these are just not even meant to be as an example questions. These are just questions that might, well, not these questions, it's just an idea. So here are 3 questions, and then, you write your answers, you submit it and try it. And please, I really urge everyone to try it, try whether it works, because if it doesn't work here, then there's a good chance that the online exam will have a problem for you as well. So this is also for me to double check that the exam technique is in fact functioning. So this will be open. Well, it says here it's until Christmas Eve. Oh, okay, fine. Try it out. Try to see if it works. And what will happen here is that now below here there will be a link which won't be open to you until the time of that exam, right? So you can then open up that at exactly the time when the exam starts. It will be below here in this section. It will appear here. Okay? Does that answer your question?
Yeah, it was already answered like a couple minutes ago. But I have one more.
Yeah, sure.
About these extra points that you promised to give.
I have them put on paper. I haven't yet. I have a paper here somewhere where I have marked the person's names who have gotten these extra points. As I recall, you got at least one from
for like the 3rd one, I think.
Yeah, you have one. I don't have it right here, but I have it on paper. I have kept the paper list, and when I'm going to calculate these points, then 1 extra point will be given to everyone who reported an error.
Okay.
That is good. I didn't have it online because the grading system here, I don't want to interfere with that. I will, and you know who you are, and if you feel like you didn't get it afterwards, if you feel like you maybe didn't get enough points, then tell me. I will try to. There's one problem is that I can give you all the information. You will receive all the information that is there, so that you can get to see the points you accumulated from the exercises. You will get to see the points you got from the exam. And then I will give you a formula that tells you how those points determine the outcome. And then into that formula, into the exercise points, I will add, well, I'll explain how I add these extra points to that. And I'll give that is in the formula. So it's in the form of f, x, y, z, where x is the exercise points, y is the exam points, and z is the extra points you earned. And then, that is a number, and then how that number translates into your grade. I cannot put this f of x, y, z so that you can see what the function is. I can give you the formula and you can check what your grade should be based on what you know. And if you get a different grade, then come to me. But what I cannot do, because I don't have a method, I don't know how to do it in such a way that you don't see each other's points. I mean, I could compile an Excel or something like this, but
we could do it with student numbers maybe. Then
well, technically, we've been told that we shouldn't really use student numbers in the communication.
Yeah, I didn't know that.
The reason is if you attend many enough of these courses that have about 20-30 students, then eventually you will be able to able to deduce at least some people's student numbers. This is ridiculous. I mean, the laws in Finland regarding these kind of registries and these kind of identifying numbers is so ridiculously strict, and I just don't want to violate those.
Yeah, that's understandable as
yeah.
well.
But I mean, I promise you all the information you need will be available for you so that you can check that you have been treated as it's supposed to be.
Yeah. So in the exam papers, do we even need to write the student numbers or?
No. You don't read. I don't think you need to write anything because the Moodle makes sure that I see
Okay.
who
Yeah.
submitted what. So
Yeah.
you don't need to. I don't think you need to write anything in the submission.
Yeah. Okay. Okay.
Yeah, because I will be able to see who it was who wrote what. So yeah, you know, no need to put anything. Just write it. Maybe write it on by hand and submit a picture. Or if you want to use LaTeX or something like this fancy thing, there's this page called "If it's in LaTeX, so it must be true." It's a joke again, you know, because in LaTeX you can write mathematical formulas that look so fancy and professional that it's very convincing, and it can be complete nonsense. But in any ways, you know, if you write it by hand or you write it in textual format, anything that is readable and understandable, then is fine. And I will review those and you know, your submission that comes through Moodle. So you get all the points you get visible by Moodle, and then I will then publish the formula which I use to determine your grade.
Yeah.
Anything
Thanks
else?
for the clarification. That's no more questions from me, at least.
Okay, thank you. I mean, I'm welcome any questions, because I'm really quite sure that I may have missed something, or I might not have said everything that needs to be said. So I'm really, you know, I really do urge you to ask if anything is unclear to you at this point. So I'm going to now stop the recording.